everyone. Welcome back to the Topos Institute Colloquium. Today we have Paul-André Mellies talking to us about the rabbit calculus. So please, the floor is yours.
Yes, so thank you for the invitation. I'm delighted to speak about this work that I developed with Nicolas, Behr, and Noam Zeilberger. So I'll go very quickly, just a little bit of motivation. I will not develop that too much, but just to say that Nicolas has a nice framework, algebraic framework, to speak about the dynamics of chemical systems and other kind of, for instance, graph theoretic systems. And it's based on rewriting. And in fact, so Nicolas constructs an algebra describing how rewrites can combine together. And looking at it, okay, in fact, we try to categorify it. And I think it does make sense to speak about it here. So really the question that is underlies this work is the question of causality. So if you look at for instance, lambda calculus, so here it's like lambda terms and beta reductions. I mean, there is a well-studied theory that tries to explain what rewrite rules creates other rules. Okay, so it's the idea that there are like cascades of rewritings. One rewrite, for instance, here will commute with that rewrite, but that rewrite A will create the rewrite C, so that in the end, here in that case, B can be forgotten, and this is the needed computation. This B here is needed, but A is not really needed. And okay, this kind of phenomena are well studied. They are important in rewriting, and here really it's I mean, trying to look at this old problem in a new way, based on this idea of rule algebra. So let me take a very simple rewriting system. So, I mean, you cannot make it simpler in a way. So you have a binary operation here and a neutral element E on the left, okay? And then you can rewrite ME X into X, okay? So it's a very simple rewriting system. Now, if we look at the rule and the terms and the way the rule can apply on, I mean, to let terms rewrite, we see that, okay, if you look at that term, there are in fact exactly two redexes, okay? So the red one and the blue one here. And in fact, they're independent. So you can rewrite one, the red, and then the blue, or the blue and then the red, because they are just independent. But, and I mean, pictorially or diagrammatically, this is exactly the situation. You have that tree here. You can rewrite blue, red, or red, blue. Okay, and you get here. But now there could be other situations where, for instance, in that tree, we have that rewrite here. But then that rewrite will create, I mean, so this is the rewrite here. It will create a new redex, okay? And so there is one redex, which is the red redex, which creates the green redex. And if we think about it, I mean, the point is the green here cannot exist without the red being reduced first. And so really it's a path of length 2, but where the second part depends on the first. And we can, I mean, if we think about it, we can say, okay, why shouldn't we consider this path of length 2 as a new form of redex, but of a new, I mean, composite rule. Okay, we had one rule here, another rule, and this would be a composite, you know, of the two rules that would produce that reduction here from that term into that one. Okay, and so you see here, I've written the red inside the green. And so now, if we want to think about this idea of composing redexes in term rewriting systems, we see that, okay, here this would be the composite rule of that first rule followed by that second rule, okay? And this idea, in fact, so that, I mean, this idea here, this simple idea, in fact, we can find it in very old works in the lambda calculus, but not formulated in that kind of, I mean, at that kind of level that I want to describe now. And these old ideas were rediscovered by Nicolas in his work on tracelets, motivated by dynamics of probabilistic rewriting. And so here, really, what I will try and show is that there is a way to think about this problem of composing rewriting rules. Express them in the language of double categories. Okay, so really it's about, I will try to justify the fact that behind that problem of understanding when one rewrite can be composed with another rewrite to produce a new reduction rule, well, we can, find double categories behind. But before I go into that question, I want to recall what double categories, mean. And I want to do it in a way that is consistent with what I will do next, okay, later. So, the direct definition of a double category, so weak double category, is that we have a category of objects. We have a category of horizontal maps. And then from this category, we have a source and a target functors, okay? And then we can compose horizontal maps. And the way it's described is using, technically, it's called an internal category in CAT. So we have this fibered product, this pullback of D1 and D1 above D0, and we map it in D1. And then we also have the identity, and they should satisfy some coherence like associativity and neutrality properties. So this is a very, direct description of double categories, but I just want to analyze a little bit more what it means. So first, we have a category D0 of vertical maps. Okay, so we have, it's really a category. We have the objects here of the double category and the vertical maps as the maps of D0. Now, we have D1, and so D1, the objects are of that form, so they are horizontal maps, and the morphisms of D1 are the double cells, okay? Now, this is the way I will draw them in my pictures. We will see it's nice and convenient to have this little picture here to represent that double cell, okay? So we have R, R prime, A, B here, and alpha in the middle. Okay, now, when we want to compose, because we want to compose horizontal maps, we need to speak about path of length 2, horizontal path of length 2, and so we have a category whose objects are horizontal path of length 2, and the way it's defined is by a pullback here. Okay, so this is a pullback here, but really is the category whose objects are of that form and whose morphisms are of that form. And again, I like to draw them in that simple way with RS here, alpha, beta, A, B, C. You find everything, all the information is here, okay? It's just a little bit more concise. Now, we can carry on that game. So we have a category of horizontal path of length 3. And so it's computed by this pullback here, or this limit. And well, it's the category of path of length 3, and then the morphisms are these like 3 double cells, and okay, and I draw it like this, okay, and then we can play that game forever. And so here this is D4, and we get. I think it's quite clear that we have now a hierarchy of categories Dn of whose objects are path of length n. And now, if we think about a double category, so a more maybe sophisticated description, but also very natural, very nice, is unbiased presentation of a double category. So it's a family of categories, okay, Dn, with a map like this, which is the composition of a path of length n, horizontal path of length n, into a horizontal map, okay, of the double category, with a number of associativity and neutrality properties. And in particular, if you look at Hn, H2 is just the composition from D2 to D1, and H0 is just the identity. So all the information is here. Okay? So Okay, and we will use that, and that's why it's good to know that we have this alternative, in fact, description of internal categories in cat, which are double categories. Okay, weak double categories. Okay, so we will be very interested in a specific double category, which is the double category. I mean, the category. I mean, the double category of double pushout. Okay. And this is really the category, I mean, or the double category we started with, because double pushouts are a beautiful way to describe rewriting systems, in particular on graphs. So it starts with any adhesive category, but think about the category of graph in particular, which is adhesive. Okay. So I will not recall what adhesive means, but I will say what it implies. Okay. So now, the objects of this double category are just the objects of, let's say, the category of graphs. Okay, so A, B, C are graphs here. Now, the horizontal maps are spans. Okay, so here A, B, S are graphs, and so here there is a span of two graphs A and B. And the vertical maps, okay, here are monos. Okay, so they are inclusions of that. I mean, here we have an inclusion of A into A prime, S into S prime, and B into B prime. And what is more sophisticated maybe is that the double cells, okay, here, okay, so they are, I mean, they require that these two squares here are pushouts, so that's why it's called a double pushout, in the original category of graphs. And so, I mean, it's not clear at all that you can, I mean, that it's possible to compose these double cells. And in particular, that if you compose two double cells like this, you still get a push out in the middle. Adhesivity ensures that. Okay, so adhesivity is a way to ensure that we can compose horizontally these double cells and that the push out condition is preserved. And the motivation, okay, the reason why people have introduced these double pushouts is that, and the intuition is that this is a rewrite from A to B, okay, and S describes the way, A can be rewritten into B. So this is the rule. And this is a redex. So this is an instance of the rule. So this means that A prime, so I will try, okay, if I can, yeah. Okay, so imagine that you have, oops, yeah, it should be able, yeah. Okay, so here we have some rewrite here. Okay, so, I mean, so we have S here. And really we think of it as some rewrite here. Okay, that's the way we think of it. Okay, and here we have a much larger graph, and we have that pattern here in the middle. Okay, and really the idea is that we can rewrite. So imagine that this is like rewritten into that. Okay, we want to rewrite that thing, okay, into that. Okay, and so the idea is that the double push out here. Okay, so so yeah, so the double push out is a way to remove. So here we remove that part, okay, in order to get here, and then we add that part, okay? And so really the two operations that when you rewrite something, first you take the part that you want to rewrite, you remove it, and you transform it into what it should be turned into is very nicely described using this double push-out technique. The thing is that, in fact, there are a few, there are different ways to represent rewriting. So some people would use double pushouts, some other would use some, other frameworks. And in fact, if we look at if we look at the very starting point of the the very starting point of the presentation, we are interested in term writing. And in fact, it's also possible to build a double category, which is a little bit more sophisticated. I will not develop it too much here, But I'm happy to answer questions later, about it. But the idea is to use some higher, let's say, higher order formulation of term rewriting so that, in fact, instead of manipulating, rewriting on graphs, we can also, rewrite linear lambda terms or terms and just do what I was showing you earlier and have some formulation of, let's say, term rewriting or linear term rewriting. So, so that means that, okay, and this is what I want to stress, is that we have rewriting on graphs, typically done in double push out, but we also have rewriting on terms, okay? And in all cases, there is a double category, okay? And so this is the level of abstraction where we want to work on. And in both cases, in fact, in all cases, the intuition is that, okay, we have here a rewrite rule that we see as a horizontal map in the double category. And then we have here some transformation. So here, okay, this is a transformation. And what we want to understand is, well, whether one specific symbolic transformation here from A prime to B prime is an instance of the rewrite rule. Okay, so it's a very, I think a very interesting and a kind of, amusing way to look at things. So what we will do is we'll try to, if you like, describe witnesses. So here the double cell is a witness of the fact that a specific symbolic computation is an instance of a rewriting rule. Okay. And what is interesting is, of course, in most rewriting systems where that we are used to, in, like, let's say, in particular in programming or maybe symbolic, algebra, when we have a symbolic, transformation, there is at most one rewrite rule that implements it. Okay. But in fact, when we move to more sophisticated situations, like maybe more operatic or where there are many symmetries, it's important, in fact, to count the number of ways a specific transformation is an instance of a given rule. And really, what we will do during all this talk is speak about presheaves, okay? So, and representable presheaf. So the intuition really is that when we have a horizontal map from A to B, it will induce a functor from D1, so the category of horizontal maps, into set, which associates to each horizontal map the set of double cells from R to U. Okay? And by the way, this will be one ear of the rabbit later. Okay, we will see that. The purpose of the talk is also to show you the rabbit, piece after piece. So this is, just one ear of it. Okay, so and again, the idea is that U here is an instance of the rewriting rule R, but the instance is witnessed by theta. Okay. So now, oops. So, yeah. Okay, and I will, in particular, in the double category that I was presenting a bit earlier, we will see that the rewrite rules I was showing you are instances of the rule R. Okay, so just to say that, okay, we are exactly in that, in the spirit, of the very beginning of the talk. And what I want to show you is how using a generalization of the convolution product on presheaves on monoidal categories, okay, so the day tensor product, we can get that equation, which is that, okay, if we apply the rule here and take the convolution product to the rule itself, but of course seen as these representable presheaves, what we will get So in contrast to, in the day, in the tradition of the day tensor product, if we take the tensor product of representable presheaves, we get a representable presheaf, okay? But here what we will get is a sum, okay, of two presheaves. The first one describes the situation where the two rules are independent, okay? So they are absolutely independent from one to the other. And the other case, so it's a sum of another presheaf where we see the representable presheaf generated by this other rule, okay? So that's the purpose. That's what we are going to achieve, okay? And that will say that applying the yellow followed by the let's say here, brown rewrite, either the two rewrites are independent or the yellow creates the brown. Or they concatenate together and they produce a new rewrite rule. Okay. If you think about chemistry, this could be one chemical operation, another chemical operation. They could be independent. So they work in different places of the computation of the chemistry, or one produces the other. So how shall we do that? So I will do a little recap on how the convolution product, for usual monoidal categories is defined, okay, and how we can, prove its main properties. And I think it's interesting in itself, and then it will prepare well for the rest of the construction. So I will take about 10 minutes for that. So when we have a covariant presheaf over a category, so here I don't speak about double categories yet, okay? Just categories. So when we have a covariant presheaf over a category, we know that we can construct the category of elements. So this is the Grothendieck construction, where it's a category whose objects are an element of the an object of the category C and an element of f of A. Okay. And then this is the way I want to draw that. So this is really inspired by proof theory. So the idea is that, in a way, F is a proof of A, you could say, and X is a witness of the fact that A is, as a non-empty F of A, if you like, okay? So for each element of F of A, we have an X here. Okay. It's just a notation, but I think it's very, again, we can think of, So, we can think of F in a way as some kind of proof system and X as a proof and A as a formula. This is really the kind of intuition we could have. Okay. So let's say we said that X is a witness of the fact that F of A is non-empty, you could say. Now, when we, and I'm going a little bit fast here. Okay, so whenever I have here an element AX and a map from A to A prime, I can push X along gamma and get a new element. And so in fact, with our little drawing, our notation, if X is a witness of F above A, we get a new witness pushed along gamma of A prime above, of F above A prime. Okay. Now, okay. Now, this is the way we define the category of elements, and this is an up vibration over C, a discrete up vibration with the projection functor, which forgets the elements, only remembers the first element of the pair. Okay, and this is well-known construction. Now, okay, I just kept that if there were questions, but I just move forward. And it's good to remember that every time we have a pair of covariant presheaves and a natural transformation between them, in fact, this is equivalent to having a commutative diagram here. Okay, so there is a very nice correspondence between presheaves and discrete up vibrations, including the natural transformations here and the maps here, which, by the way, are forced to be discrete up vibrations. Okay. And so there is a categorical equivalence, again, between covariant presheaves and discrete up vibrations above C. Okay, that's nice. Okay. But moreover, there is an adjunction, okay, between general, let's say, functors above C and discrete of vibrations. Okay, so this is called a comprehension adjunction. Okay, and in fact, this will play a role. So we can reconstruct, if you like, the deconvolution products from these ingredients. So the idea is that, okay, imagine I have a monoidal category, C, two covariant presheaves, and then this is the usual definition. I mean, if we look at using a Cohen formula, this is what we would usually find in the books, and it's beautiful. It's a beautiful formula. Okay, and okay, I just move. I mean, there are okay. I mean, there is also a way to think of it as a left-hand extension, but okay, I want to focus on that formula. Just let's spend 1 minute to think about what it means. Okay, so what it means, it says that an element of the coand is just a gamma here from B tensor A into C. So you can think of it as a way to decompose C into B and A, and then a witness of F above A and the witness of G above B. Okay, and then there is an equivalence relation given by the coand. So, I mean, this is the nice way to draw it. So, okay, we have X witnessing F above A, Y witnessing G above B. And then there is the gamma here. Okay, I mean, it's just a very natural. And you see already there is a little bit of a rabbit here. Not yet, but I mean, we're getting closer. Now, this is an element of the convolution tensor product of F and G. And the Cohen formula means that, okay, if we are in that situation here, we should identify that element with that one. Okay, I mean, and so, and this is, I mean, this is kind of, okay, well known if you study a little bit the theory of cohens. This is exactly what it says, okay, that in a way, there are two ways to interpret that diagram. They are equal as elements of the tensor product. Okay. And yeah, that's it. Okay, this is the equivalence relation. And that says, yeah, again, you know, gamma with beta y and alpha x is the same as composing these two things and then xy. Okay, that's it. Okay, and then there is this beautiful theorem that says, okay, this convolution product, in fact, equips the category of covariant presheaves with the structure of a monoidal, in fact, closed category. But here, let's say a monoidal category, which means that the convolution product in particular is associative. Okay, nice. Now, if we look at the way, I mean, how we can analyze that, there is a nice way, which is to say, okay, we start from the functor, you know, element G times element F into C times C tensor. Okay, this is not, this is not an up vibration. So we want to turn it into an up vibration. And so if we think about it, the objects here in the source category, they are just pairs like this. Okay. And now, if we want to get the free split of vibration that corresponds to the elements, really it means that we need to extend this little picture with a gamma here. Okay, that's, I mean, the intuition, because we want to get a free of vibration in a way. Okay, so that's the way to do. I mean, and then we also need to get this. I mean, so we have these maps here. Okay, so and then okay. If we now look at the connected components, the maps are turned into these equivalences, and that's why we recover. I mean, that's a way to think about how we recover the construction here. Okay, and really it's about the construction of the tensor product is really has to do with taking the tensor product in a naive way in cat over C, and then constructing the free discrete of vibration above that. Okay, and that's okay. And so okay, I just show you. I mean, this is just the story how it works, and okay, we can. Yeah. So, but the point is that when we have an adjunction like this, there is clearly a tensor product here, and the adjunction here enables to transport here. Okay, so if you think about it here, there is you know, a commonad here, and we will enable to transport that tensor product here above C into a tensor product, which, I mean, should be oplax. Okay, so, you know, there is some, I mean, we can transport along adjunctions, but we turn oplax structures or general, I mean, like weak structures into oplax. But the good thing is that in the case of the tensor product, we get a very nice structure, which is pseudo or weak, but which is much better than being oplax. Okay. So now let's try and do the same for double categories. So, I mean, really it will be the same construction, but now instead of taking tensor product, we will look at composition of horizontal maps. Okay, but what I will tell is really a straightforward generalization. Okay, if you accept it. So we have this really replaces the tensor product, if you like. Yes. And so we have this functor from D2, so the path of length 2 into path of length 1, which is composition. And now we can define, okay, so if you look at it, so if we have two presheaves over D1, we can, to every horizontal map, associate that coend, which consists in decomposing T into R and S, and then looking at witnesses of R, I mean, of F and G above R and S. And so I will describe it now, okay? Just in the same way as I did. So an element of the coend is, okay, a double cell here from R, I mean, RS into T, so you see it here, plus a witness, I mean, an element of G of S. So I said it's like a witness of G above S and a witness of F above R. Okay, modulo an equivalence relation that I will describe later. And this is where we get the, you know, the rabbit. So, I mean, you know what I draw here in this coend, an element is really something of that shape. So it's a decomposition of T into RS, okay? And then a witness X of F above R and a witness Y of G above S. Okay, this is exactly what I drew, and this is the way you should understand it. So the intuition is that, if you like, we are computing a new presheaf from the F and G by taking every horizontal map. We try to see how we can decompose it in two, and then take you know, a witness of the first presheaf above R and a witness of the second presheaf above G. Above S, yes. Okay? And that's really the recipe. But now, if we look at it, okay, there is the coend which says that if we are in that situation, okay, so it's like we decompose the rabbit into, you know, gamma, alpha, beta, and yeah. If we plug everything together, we want that composing gamma with alpha, beta here, followed by the witnesses X of F and Y of G, it should be equal. So we force the equality, if you like, with this gamma, but now the gamma with the witnesses beta Y and alpha X instead of X and Y. Okay, so this is the coend here that does the job of forcing that equation. Okay, good. So now, and this is the key observation that emerged from, I mean, discussions that we had for many years with Nicolas and Noam. I mean, it was a very long, slow, and exciting process at the same time. In fact, this thing I've shown you here, so this operator here on presheaves, so this one, okay, so this formula, in fact, will induce an oplax monoidal, okay, let's forget closed, oplax monoidal category. And so let me explain what oplax means here. So the observation is that what we did for 2, we can do for 3, 4, 5, okay, n. And so when I have, you know, F1, Fn, so n different covariant presheaves, I can merge them together, I mean, and using, I mean, n-ary convolution product. So for instance, in the case of 3, I can do that. So HGF maps every horizontal map into a decomposition of U in three, and then three witnesses of, one witness for R, one witness for S, and one witness for T. Okay, so it's a decomposition in three. It could be decomposition in 4, 5, N. And so this is the like, okay, it's the rabbit with three ears here. Okay, and this is now an element of the ternary tensor product of FG, H here. Okay, so X, Y, Z are witnesses of F, G, H above R, S, T, and here there is a decomposition of U into R, S, T. Okay. Now, same story as before, the Cohen enforces that equation. And so now, and this is, I think, one of the most amusing part of the of that work, is the observation that in fact this is not associative anymore. Okay, why? Because clearly, if you are of that shape, okay, so it means you synchronize your decomposition of U, okay, you are, of that shape in the sense that if you can, in one tick, decompose U into RST, you can, clearly decompose it first into here VT and then V into RS, in two ticks. Okay, but it's not, here, if you can decompose U into that shape, doesn't mean you can decompose it into that shape because of the G here. G is non-trivial. Okay, so really, this shape is a specific example or instance of that shape where G is, let's say, identity. Okay, and so it's not, these are not isomorphisms. On the other hand, it's perfectly associative. And so, okay, so this is what I was explaining. If you are of that shape, you are not necessarily of that shape. And so, a lot of the work we've done with, Nick and Noam was to give, once this was observed, to give sufficient condition to ensure that the convolution tensor product is not just oplax, but it's pseudo, or weak or strong or whatever. That in fact, we have an isomorphism. And so what I will show is we want to find a sufficient condition so that the associativity maps here are in fact reversible. Okay? And remember that what we're doing generalizes the usual day tensor product. So there should be a nice condition that enforces that these associativity maps are weak. And this is the condition. And I will start by giving a very general intuition, but I think the intuition now, the challenge was then to formalize it, to write it, to find a good conceptual explanation. But the intuition is very simple in a way. We want, we want that shape to be turned into that one. Yeah. This is what we want. So we want to turn any time we have that shape, which looks like a rabbit, with like, okay, we want to turn it into that, that animal. So let's suppose, okay, that we can always turn every double cell of that shape, okay, into that decomposition, where this is identity. Okay, imagine that we can do that. Okay. So it's of course, it's a quite, strong property, but still, imagine that we can do that. Essentially, it means that when we have a double cell from a composite, RS, we can factor it into alpha beta, followed by a two cell. It's not a double cell. It's really like here. It's a cell of a two category. Yes. So we can reduce, if you like, the double cell here from RS to T into two double cells, followed by a two cell. Okay, imagine that we can do that in some way for some reason. Then, if we look at that shape, well, let's apply it to gamma. So we decompose. Now we are here. You remember there is this coend that enables us to look at things like this. Okay, and so now, if you think about it, now we can compose lambda and delta, and we get that picture, and we're done. Okay, so really the challenge is to understand, how to express properly that equation. Because we want it to be, we want an elegant formulation of it. And so this is where there is a kind of, pleasing kind of explanation, okay, which I think is, okay, so it's nice to explain here. So I have about 10 minutes now, okay? So I will explain the cylinder categories and maybe some. So, okay, so if we take oh, sorry. Oh, yeah, sorry. Yeah. So if we take a double category D, general double category, in fact, it comes equipped with a family of categories that are called the cylinder categories. Sorry, I have a problem with I don't know what's going on. Sorry, it's, okay. So the objects are that shape, okay? So they are the top of a cylinder. This is a path of length n, identities here, and a path of, just one map, okay? That's the objects. The cells are, because we are building a category, so that's the objects. And the morphisms from sigma to tau are of that form. So first we want to have, that. So here we have sigma and tau here. Okay, so we want to have a map from sigma to tau. It will be described as a tuple of double cells here and one double cell here, making a diagram, some equations. So this diagram should be equal, or this double cell should be equal to this double cell. So it's a little bit hard to understand with, in the general case n. So I just look at the case 2, and it should be clear. So we have, this is an object, sigma, this is an object tau. Okay, so they are the top and the bottom of a cylinder. And what is a map, a cylinder map? It's a pair of phi here, which is a double cell on the outside, and phi 1, phi 2, which are a pair of double cells on the below, if you like. And the equality I was showing you is just saying that, they should be consistent in the obvious way, okay? So if we take S1, S2 into S and then followed by phi, it should be the same as S1 followed by phi 1, S2 followed by phi 2, composed with tau. Okay, so that's a very basic, a very natural equation and construction. This defines the, a family of categories. For each natural number, there is one category called a cylinder category of D. Okay. And the nice thing is that if we look at Hn, which goes from Dn to D1, we realize that this composition, remember this is the NRE composition, factors, in fact, in that way. So first we can map Dn into cylinder of Dn. Then, here, remember, in cylinder of Dn, the objects are of that shape, okay? So we can just forget S1, S2, and then map S into S here. Okay, so this is like the projection. And so it's so, if you can think of it as some kind of weak way, to compose. We start by composing things, but in a larger place, and then we map into D1. And the definition I will take is that a double category satisfies the n cylindrical decomposition property simply when the functor pi n here is an obfibration. Okay, this is a very formal, definition, and not necessarily discrete. Okay, but the theorem is that when we have that property, then the convolution product is not just, oplax monoidal, but strong monoidal, which means that we really have this, and the associativity maps are reversible. Okay, and so that's the main theorem, that if we are in that situation, so and maybe I can discuss that later what it means, but really the vibrational property of pi n says that. Okay, and maybe we can discuss that later. But this is a kind of conceptual way to speak about the decomposition property. Okay, so now this is the main theorem, and yeah, and so now if we look at the examples, the theorem applies to, every bicategory okay, satisfies the property. So that means that when we are back to a situation which generalizes the tensor, I mean, like monoidal categories, because the monoidal category is just a bicategory with one object. In fact, we have a nice generalization of the dead tensor product, which is exactly monoidal. Okay, not oplax monoidal, but exactly monoidal. But also every frame bicategory for n larger than one, and then every double category. This was our main, objective. I mean, to look at this kind of, double push out or linear term rewriting systems. So this, this kind of double categories, which we are interested in for either for conceptual reasons or for rewriting, they satisfy the property. Okay, so that means that in their case, the dead tensor product, the convolution tensor product, is really a monoid. I mean, it's a monoidal construction. And so just to show you a little bit, what it means to, I mean, the rule algebra.
You asked me to interrupt you at 45.
Yes, yes, and you're right.
Okay,
You're
okay,
right.
thank you.
Yes, perfect. Thanks a lot, David. So really, so in the case of rule algebra, so the idea is to, I mean, so this was developed by Nicolas Behr. So it's a way to organize rewrite rules and to see them as operations on, let's say, graphs or terms, okay? And these operations can be composed. And the idea was exactly like I was showing you, that if we take two rules, we will look at all the, if you like, possible ways to apply the rule R followed by the rule S. And here, this means that when we compose the two rules, we just sum all the possible admissible matches of the rule R against the rule S, if you like. And so this is what we now get, in our categorification. If we take the two representable presheaves associated to the rules R and S, so if we apply R and then S, we will get a sum, okay, of, representable presheaves in good situations, okay? So this is what we want. We want to find conditions so that it's not just a co-limit, as it should be, but really a sum. And in fact, there are conditions which have to do with pattern matching. So it's something which, and not just pattern matching, unification of rules that can be expressed. So we developed that in the paper, if you want to have a look. And in fact, okay, I just want to say that under some very reasonable conditions, and I want to show, the kind of picture. So, we want to analyze how a rule R1 can be composed with a rule R2 in that way. So really, this means this is the rule R1. This is the rule R2. This is the instance of R1. This is the instance or an instance of R2. And we want to understand, this, how this rewrite can be seen as an instance of the composite. And in fact, looking at very carefully at the different ways these two, okay, because here it says that B and C can be embedded into a larger X, which contains then both, and maybe B and C will overlap. And so here we have, if you like, a calculus of overlaps that enables us to say that, in fact, each overlap is independent or incompatible with the other overlaps, okay, to get the sum formula. So anyway, based on simple conditions, we can prove, in particular, in the case that I was showing you at the beginning, that if we apply, you remember the term rewriting system, so in the double category of term rewriting system, if we apply the convolution product to the representable functor generated by the rewrite rule R that we saw, if you remember, m of ex rewrites to x, then we get that sum, and this is exactly what I was showing you. So this is the representable presheaf for the rule R, again. And now if we take the convolution product of the two, we get this kind of, like rabbit shape. And if we analyze the way, the generators of the rabbit shape, we see that either the two rules are independent or one creates the other, okay? And this is done by some kind of calculus of, categorical calculus of unification. Okay, and so that's it. just to say that we have a categorification of these traceless and rule algebras that Nick introduced, and also that works for many frameworks. So this is the nice thing. It's general to double categories. So it's part, if you like, now. I mean, I would say it's part of the basic toolbox that we can have and use for double categories. And then we have a convolution product, and we have the cylindrical decomposition property that ensures strong associativity. So the thing we want to develop is to have, to look at higher order rewriting systems, to develop also the stochastic aspects, more quantitative and stochastic aspects, and then really improve our understanding of causality in rewriting system. And this is a nice thing, that causality and the idea of causal sequences of rewrite has to do, in fact, with analysis of stochastic aspects. And I want to stop here. I'm very grateful. Thank you.
Thank you. Okay, we have time for questions. So if you have a question, either raise your hand in the chat by pressing the reaction button, raise your hand, or type something into the chat, or just unmute yourself and ask. Let's see here. Valeria.
Hi. Hi, Paul Andre.
Hi,
It's a
Valeria.
completely stupid question about references. When you said that the term rewriting of linear terms on this category LTRS, what's the reference for that? Is that Nicolas Behr stuff? It's your stuff?
So this is yes, something I'm happy to share with you, but I'm not sure it's written anywhere except on the slides, probably. But yes, this is something that we want to develop further, and in particular, so maybe I can say a little, because yes, this is something I'm very happy in particular to share with you, if you're interested. So
right.
so
Yeah.
just say, I mean, it's really based, if you like, on this idea that we can use second order, lambda calculus. I mean, like Jan-Willem Klopp combinatory rewriting system. So we can use them to, sorry, this is push out, yes.
Yes,
So,
that's the one, yeah.
so yeah, we take a signature, okay? And so the idea is that we construct a double category whose objects are sequences of linear lambda terms. They are closed, okay? So they are formulated in a context.
Right.
And the types are very specific because they are continuations. So you just write things like this. So you have a tensor of negated types. Yes.
Right.
And then each of the constant has that. So it's really like church also, church encoding. So every letter of NRE letter is seen as a function, if you like, with n. And okay, and then the vertical maps are, if you like, inclusions. Just like what we and you see the maps here. We have these terms here, and in fact, we want to kind of separate the context and get this substitution here. So V1 here is F1 of okay. And then the thing is that the rewrite here, so the double cells, because remember we want to have the rewrite described as a double cell. By some kind of the magic of the lambda calculus, we can turn the rule here into a general instance, and that's what the F1 FQ here do. Okay, so they provide the context in which the rewrite can be done. And so I think I have this example just to show you. So this is the rewrite from MEX into X. Okay, so this is it's supposed to be the rule, yes. And then the substitution, if you want to substitute here, you see we need to, we have the U here, and it has to be plugged here. This is the place where the rewrite will occur. And so the idea is that we will plug that in the context, so it will appear here, and it will be able to perform the rewrite. And interestingly, this is the same context here as here. Okay, so it's really like second order context in the style of Jan-Willem Klopp, for instance. Okay, but formulated. I would say also it has to do with higher order abstract syntax. Yes.
Right. Yeah, no,
But I'm sorry, this part is part of the slides. It's nice to explain, but it should be written. I mean, you're right. So it's not a question, it's my own, our own, yeah.
Oh, great. I thought it had been written somewhere. It's just that I did not know about it.
No,
But
no, no. I mean, I would love that, but yeah.
yeah, great. Thank you. Thank you very much.
Thank you, Valeria. Looks like Xiaowei has a question.
Well, hi. Hi, Paul Andre. Thank you for the beautiful talk. Really enjoyed it. I'm wondering about your CDP, cylinder decomposition property.
Yes. Mm-hmm.
It seems like at least the rewrite systems that we care about, they all have CDP.
Mm-hmm.
And I'm wondering if you know of any rewrite systems that doesn't satisfy CDP but are still interesting. Like, for
Yes.
instance,
Yeah.
like the example I'm thinking about is like, for instance, refinements of programs and things like that.
Yes, yes, yes.
Do they satisfy CDP or are there interesting examples that don't
It's a
satisfy?
good question. So I would say that okay, so there are two traditions, okay, that we are merging, or three maybe you could say. So there is a graph rewriting, okay, based on this like categorical graph, or let's say categorical rewriting, double push out, okay, and here it works well for the let's say traditional examples. Then there is the rewrite, and we have this nice story for term rewriting. We would like to extend it for high order, and it's something which should be done definitely. Yes. So I mean, the examples you have in mind, they would need to have typically high order. I mean, if we want to deal with functional programs, and yeah. So this is something, but I would say, okay, so that we can take the philosophy, of oplax. So it's something we don't maybe do often, but in fact, so the first theorem before we go into this, sorry, yes. So the first theorem was that we get yes here, yes, that was here, yes, here. So that the theorem is that this family of convolutions, I mean, has the oplax structure. Yes, I think that it can be interesting to know that. I mean, already, because this is already very strong oplax monoidal. It means that we have all the coherence, and there are many situations in logic where oplax monoidal structures are important. So for instance, when you start to work with continuations, double negation, you get very quickly oplax. So for instance, the historical definition of disjunction for continuations, like negation of A, tensor negation of B, and you negate again, so it's a disjunction. It's not monoidal, it's oplax monoidal or lax monoidal. So what I mean is that you have the structures which you can work with, okay? And in fact, a lot about programming has to do with the fact that sometimes the structures are not exactly monoidal; they are lax or oplax monoidal.
Right.
Okay,
right.
and then there are coercions and everything works, but we need to be a little bit more careful about the coercions. I mean, okay, just to say, in just one word, in programming, we love adjunctions. And there are not equivalences. And adjunction means that there is a little gap.
Right.
And this is the same gap, you could say here, in a way.
Okay. Okay, that was helpful. Yeah, thank you so much.
Okay, it looks like we have time for one more question. Maybe Jacques, correct?
It's actually Reed and Jacques here.
Oh, hey, Reed.
Yes. So
Hello.
just had a quick question about the cylindric decomposition. So it looks very simplicial, and I think it gives you a simplicial object in cat, right? Have you guys considered like any of
Yes,
ways
I mean,
of
this one,
generalizing this to
yes.
higher order rewrite or higher dimensional rewrite systems or anything like that? Because
Yeah. So, it's a good point that, I mean, you mean here, yes? That's what you're saying about this decomposition here. Yes. Yes. Yeah, of course. I mean, this was really the kind of guideline, yes? We have simplicial objects, and we need to organize them in some way. And but I would say that, okay, I mean, like we have this formulation which enables us to express it in the language of up vibrations. We use, I mean, we can prove the theorem about the fact that the associativity are reversible using the fact that it's an up vibration, at some abstract level, like two categorical abstract level. And clearly there is more behind the story. I'm convinced, yes. And you could say, okay, maybe I should say that there is I mean, the motivation really, okay, I mean, maybe it's worth saying that. There are two main notions of vibrations in, let's say, category theory. There is the usual like Grothendieck vibration, but also the street one. And really the purpose, I mean, if you look at yes, this property here, okay, this says that the multiplication, the composition, is something like a street of vibration, except that now, instead of having general isos, we have a lambda. Okay, as a matter of fact, in most of our examples, lambda is an iso. But what is important is this is strict here on the left and the right. These are identities. So really the condition we're giving is a generalization of both Grothendieck and street by saying we pick a class of specific maps. Okay, and that's also a way to think of it, yes. And in the paper, it's formulated like this also. I mean, the cylinder is good for explanation, but really there is a general abstract notion of what it is to be a weak notion of vibration, but where weak is parameterized by a class of maps below. Yeah. So here in that case, it's not just ISO. There are maps with, I mean, two cells. Yes. And this is why also it took us so much time because we thought, oh, this is, at the beginning, we thought, oh, this is a street vibration. I know it's not a street vibration. I mean, yeah. So we needed to kind of, cook something.
Well, I will give the paper a closer read then. Thanks.
Thank you, Reed. Okay, well, that's all the time we have. Thanks again, Paul-André.
No, I'm grateful. It was really nice to interact like this. And if you have any question and comments, you can email, of course, I mean, me, but also, I mean, Nick and Noam, we are always happy to interact. Yeah.
Okay, great. So I'll go stop the live stream.
Okay, so I'm here in the next 5-10 minutes if you want to, I mean, even, I mean,